All right, in case you missed the notes in class, page 6 is where we get to look at how energy can get involved with our stoichiometry that we're doing. And what you need to keep in mind is energy is a part of every reaction. We're either going to be gaining or losing energy. There's no reactions that really have zero change in energy. And that means that we can take those energy terms, those delta H numbers, that up until now we've been kind of seeing separately from the reaction itself. If we have a reaction like this AX plus B making A plus BX, normally we've seen that enthalpy term just written off to the side as some kind of delta H number, completely separate from that reaction. But we can actually put that kilojoules number in the reaction, have it act like a chemical on either the product or reactant side. And when we do that, because everything in our chemical reactions always has plus signs in them, that might mean that we lose some of the information that we would normally be looking for, because that positive or negative sign helps us tell the direction that that energy is going. So when it's in the reaction, even if it's being lost or gained from our reaction, it's going to have a plus sign around it. So when we talk about energy, if it's in a reaction, if energy is a product, meaning it's being produced, it's coming out of our reaction like the products are being made, then the reaction is exothermic. The energy is leaving, coming out of our chemicals. If the energy is a reactant, then that means it's going into the reaction, into the chemicals of the reaction, which makes that an endothermic reaction. Now, if we look at a reaction, a classic reaction that you probably recognize from biology, this is cellular respiration, where our cells take in glucose and oxygen and turning it into CO2 and H2O, as well as some energy. So this is how our cells create energy for the rest of the body to use. And notice how, because this energy term, the kilojoules, is on the product side, it's after the arrow part of my chemical reaction, then that means energy is being released. If we reverse the reaction, and I'll write that out for you just so you can see it, and you definitely don't have to copy this down. All that I've done here is take what used to be our products and make them the reactants. What used to be the reactants, turn them into the products. Just switch the side that the chemicals are on in each side of this reaction. Notice now our kilojoules term is before the arrow. It's a reactant, so it's going into our reaction, and that energy is being absorbed in order to produce glucose and oxygen. So just another example real quick of how we flip the reaction, and what's happening with our energy is also going to be flipping. Our main focus here on this page, and we'll come back to that idea of endo, exo, and reactions and looking at those energy terms in just a minute. But the main focus of these notes here on this page is how we can do some stoichiometry with energy. And remember, stoichiometry is just about using these balanced chemical equations in order to be able to convert between substances involved in a chemical reaction. The only difference here with energy is that it's not always going to be chemicals that we're converting between. All of these questions are either going to ask you about energy or give you some information about energy and ask you about a chemical. So instead of going from how much glucose would it take to create 57.2 grams of oxygen, going from two chemicals, one to another, this question is asking how much heat energy, so we're going to be using these kilojoules, is released when 1 mole of glucose reacts. And even though we don't have the number 1 here, if we just have that formula there with no other number in front of it, we know it's understood to be 1 mole. So even without any true stoichiometry, we can see that 1 mole of glucose would produce 2,560 kilojoules worth of energy. Now, if we were to show this using stoichiometry, I could take that 1 mole of glucose as our given, and then I would have to use this 1 to 2,560 kilojoule ratio, making sure to put the glucose on bottom, and then that 2,560 kilojoules on top. This used to be what we would call a mole ratio, but because there's moles on one side and kilojoules on the other, it's really just stoichiometry. It's a mole to kilojoule ratio. But that's all that we really need to add. That's the only new stuff that I'm trying to teach you about on this whole page. All the rest of the Stoic stuff, especially when we see grams, is going to be the same. We just need to recognize we can use that kilojoules as part of our ratio, even if it was written separately from the rest of the reaction. We can include that as part of our ratio. So obviously, if I do 1 times 2,560 divided by 1, our answer is 2,560 kilojoules, of course. Now, this next one, we also could probably figure out in our head without doing a full stoichiometry problem, but stoichiometry can help us see and kind of reassure us we're doing it the right way. This is some nice whole numbers. We're given, and kind of 3 moles of oxygen is reacting, and we're asking how much heat is going to be released. So, because it's giving me information about oxygen and asking me about that energy, I'm going to be using this 6 to 2,560 ratio in my problem. And you might be able to look at this and say, well, I'm putting in half as much oxygen as the reaction needs, so I'm going to make half as much energy, which is true. But if we set this up with our stoichiometry skills, starting with the given from the problem, as always, the next step is going to be to put the number of oxygen molecules, moles of oxygen from that balanced chemical equation down on the bottom, because we started with oxygen. The diagonal rule says we got to put the same stuff diagonally down from our starting point, which means just like the last problem that asked about our energy, we're going to be ending up with the kilojoules up on top. And here you can kind of see that 3 over 6 is 1/2, essentially 1 over 2. So we are doing 1/2 times the 2,560 number, which is 1,280. And if you do 3 times that number divided by 6, you'll get the same answer. Kilojoules, of course. If you're wondering why I'm keeping so many sig figs when both of these technically started with 1 sig fig, it's because I didn't think through my sig figs when I wrote these problems. It technically should. If we start with 1 sig fig, our final answer should get rounded down to 1 sig fig. But we don't want to round these that much here. So we're going to pretend we don't have sig figs rules for right now, just for one more problem, and then we'll bring that back when we start with the kind of more formally written problems. So in this next problem, not changing slides yet, we're kind of reversing the reaction, so we are going from our carbon dioxide, water, and energy and trying to produce some glucose, but it doesn't really matter which direction the reaction is going. We can do the math either way here because we are starting with 12 moles of glucose. That would be our starting point for our stoichiometry, and then we want to focus on the glucose and our energy. It's actually going to be the exact same ratio that we used before. Just going to bring that down. C6H12O6 makes 2,560 kilojoules of energy. So, same relationship between the energy and our moles. We're just going a different direction with the reaction with a different given. But if I do 12 times that number, we get a very large number out. Once again, let's just keep all these digits for now. And that's our answer. So hopefully this isn't seeming too bad yet. We are going to make it a little more complicated in those problems down below. Definitely not stuff that you'll be able to do in your head. But even at this level, this is most of what we're doing. Now, let's take a quick break from calculations. These 2 problems here in the middle of the page just want to kind of bring back that idea of looking at our reactions, and specifically when the energy is part of our reactions, and figuring out what sign to expect on the enthalpy and what type of reaction it's going to be. And honestly, I think the first place to go would be find the type, because I can see that that energy in that first reaction is on the product side. It's coming out of my reaction. It's exiting my reaction. It's going to be exothermic. And then I feel like I can go back and think through, oh, what is the delta H going to be? If it's exothermic, this will be negative. Even though there's a plus sign in there because it's part of the reaction, if we wrote that enthalpy value separately from the reaction, it would have a negative sign on front of it. this next reaction because the energy's on the reactant side. It's going into our reaction with that calcium carbonate stuff, which means it's an endothermic reaction, and we would expect the delta H to have a positive sign. So next, we're going to do 2 more problems. Like I said, these are going to be a little bit more complicated, but not much. And before we actually do question number 2 here, I want you to go ahead and make this quick change like I see, like I've made on my screen here. I want you to cross out all the way from the word amount, leave the words calculate to V, and cross out all the way through that 3.75 number. So now this question is asking us to calculate the moles of aluminum oxide decomposed, and now add at the end of that, kind of off to the side. I know you don't have quite as much space as I do on this next line, but we need a given for this problem. We want to find how many moles of aluminum oxide decompose when 527 kilojoules of energy is used. And I need you to do this kind of rearranging for this problem because I need you to see a problem where we're starting with kilojoules. And this really isn't that much more complicated than what we were doing, but I want you to have an example written down of this so that you don't think that it's weird or hard to start with kilojoules. Because here, just like with all our other problems, because it's giving me information about that energy, those kilojoules there, then of course our kilojoules are going to be part of our stoichiometry process. Because it's asking about aluminum oxide, then the Al2O3 stuff over here is going to be the other part of our moles to energy ratio. So we're going to be using this 2 to 3,352 ratio in our problem. That's all that we're going to need. But because our given in this problem is the 527 kilojoules, as we start trying to get to the aluminum oxide, then I need my kilojoules number to be down here on the bottom. So we're going to be putting 3,352 kilojoules down on the bottom, and then 2 moles of aluminum oxide on top. So same type of problem that we've been working out using this ratio straight from that balanced equation, just energy and whichever other substance it's either asking about or giving you information about. And we're done. So, well, we need to actually calculate this answer, and I'm going to write out my kind of unrounded answer here because this is when we're going to be bringing back our sig figs. So our unrounded answer with a couple extra digits here should be turning out to be 0.314439. And if we look at our given, because this was 3 sig figs, we only want to keep the first 3 sig figs. And leading zeros are not sig figs. They're just placeholders to make sure that that decimal point doesn't get lost in all the other work that you're doing. So if I'm rounding this to 3 sig figs, then 0.314 is going to be my final number answer. And this is not kJ, this is not kilojoules here, because we were asking how many moles of aluminum oxide would be decomposed, and we ended up with aluminum oxide there up on top. Our final answer is going to be 0.314 moles of Al2O3. So hoping that flipping it around like that doesn't suddenly confuse you. Same idea, just starting with kilojoules. This last problem is going to get a little bit more complicated, and this is where we do, if you were wondering, why did I even pull out my periodic table? It's because once we see grams involved in our stoichiometry, we're going to need those periodic table numbers to turn our grams into moles. Because even though I know I want to figure out from water how much energy is going to be involved, I need to have this as moles before I can use this 2 number. That is a mole number. So I have to turn my grams into moles before I can turn those moles into kilojoules. So we are going to start with our given, of course, 15 grams of water, and then using the periodic table to add up 2 H's and 1 O, we get 18.015 grams of water. Keep in mind, the opposite side of our grams is always 1 mole of that same substance. We don't use the number from the problem yet. That number is only going to get used when we put it with the kilojoules number. And we can do that next, because we're not done until we get to kilojoules. We've got moles of water, though, finally, so we can put the moles of water down on bottom. Since water was up top, diagonally from that, we need some more moles of water. And then we can finally finish this up and end up with the kilojoules that it was asking for. And my unrounded answer here was 238.134. And here we did have a 3 sig fig given. That 0 at the end of our number, because there's a decimal there in this number, that is a 3 sig fig number. That 0 is important. That 0 helps us know we measured something more precisely. So 3 sig figs to start with, 3 sig figs to end with. So essentially just rounding this to a whole number, 238 kilojoules. So that is officially the last stoichiometry notes that we are ever going to take in this class together. There are a few problems that we had a little bit of time to work on in class. You do not have to complete these outside of class if you haven't already been in class with me taking these notes, but I would recommend that you try. This is about our halfway point in the unit. So we're going to be finishing up the unit pretty soon and then testing. So if you can try some of these, there's not too much new to this stoichiometry stuff. So I would encourage you to try to work these out. And one thing that I want to point out, the reason I made this slide here, is that a lot of these problems have that separate enthalpy term again. We've written it apart from the chemical reaction, but it doesn't change the value at all. So we can still use that number as part of our ratio, since it's giving us information about sulfur and asking us about heat, that energy. We're going to be using this 2 to 791.4 ratio somewhere in this problem. But I am noticing some grams, so make sure that you turn those grams into moles first. It's going to be a lot like that last problem that we just worked out. The other thing that I want to make a note of, because we have these enthalpies written separate, they do have negative signs in front of them as well. So if you use that negative sign in your calculation, then your answer should turn out to be negative. But I normally don't include those negative signs, not because I'm making it positive. I'm not changing it from endo to exo. But keep in mind the negative sign is just telling us about the direction the energy is moving. There is no such thing as negative energy, just energy being lost or gained. Just like there's not such a thing as a negative mass or negative weight. Nothing can ever weigh -1 pound or even -1 gram. So there are some quantities that can go negative, but energy isn't one of them. The negative sign we have just shows us a direction. And because the direction is already being specified in the question, it says how much heat will be released. Just like if I asked you, how many oranges did you drop? You wouldn't necessarily say -5 because you lost 5 oranges. That does tell us a direction, but it seems like a weird way to answer that very normal question. Oh, I dropped 5. Like there's 5 less in my bag than it was before. We don't have to use a negative sign in every context to show that direction, especially when the question we're answering already specifies that direction. And one of the biggest reasons why you will not see any of those negative answers in my packets for any of these kilojoules is actually because of questions like number 4, where we do have a negative enthalpy value. If you plug this in though, because we're solving for grams, if you use a negative kJ in this calculation, you're going to end up with -720 grams. And like I said, grams can't be negative, and it doesn't even make sense. It's not like we're losing 720 grams. That's the 720 grams that's going into our reaction. So the negative does not make sense and would actually lose you a point on a test or quiz if you do include a negative sign on something that cannot be negative. So in my perspective, it is more correct or kind of safer for you to just always keep your kilojoules number positive when doing stoichiometry. I'm not saying it's always positive in every context. If we do our calculations with a positive value, we still see that negative sign there. If we were asked a follow-up question on any of these, is it endo or exo, we could answer that from the original reaction. We wouldn't even need to do the calculation to answer that. So if that part confuses you, do the best you can. If there's any confusion about the sign or any of these values, please come in, ask me questions. I've got all of these problems worked out in my packet, and I would love to help you finish out the final stoichiometry stuff of the year. this, and then we're done with it.